Welcome to the Exam Tower. I am your tower director for this tactical briefing, and today we are running a high-stakes live simulation on securing those absolutely critical method marks for Cambridge Mathematics AS and A level. Specifically, we're locking our radar heavily onto topic 4.4, that's Newton's laws of motion, focusing squarely on the fundamental equations F equals ma and weight equals mg. Now, listen, if you've ever felt the extreme time pressure of a Cambridge exam bearing down on you, feeling exactly like an incoming heavy aircraft that's coming in way too fast, you are absolutely in the right place. We are going to treat this entire explainer as a simulated air traffic control exam emergency. My mission here is to teach you exactly how to manage that intense pressure, how to strategically prioritize high-yield marks, and ultimately, how to safely land your grade without crashing and burning. Okay, let's dive into this reality check right now. This topic appears in every examination series. Literally every single time you sit down for a mechanics paper, without fail, this incoming heavy aircraft is going to pop up on your radar. Mastering Newton's laws, understanding exactly how to deploy F equals ma and weight equals mg is not just some casual suggestion from your teachers. It is a strict, non-negotiable requirement if you want to clear the runway and achieve those top marks. The examiners know perfectly well that this is a cornerstone of mechanics, and they're absolutely going to test your limits on it. So to manage that test anxiety, we're taking a structured 5-point flight path straight into the mind of the principal examiner. We'll start with the exam reality, move into core theoretical foundations, outline the method mark strategy, tackle systematic problem solving, and finally look at the top 3 examiner alerts. Let's get to it. Section 1. The exam reality, decoding the cognitive domains. We need to identify the absolute primary obstacle candidates face when they're sweating under exam pressure, frantically trying to pull full marks out of a complex, multi-part mechanics question. The ultimate challenge flashing in red on our radar grid right now is applying concepts to unfamiliar contexts. To explain this, let me tell you about 2 specific operators we constantly monitor in the exam hall. First up, there's router Alex. Now, Alex gets completely bogged down in the minor mathematical details. He creates this infinite holding pattern of rough work, constantly second-guessing and recalculating the exact same frictional force 3 different times. He burns all his time. Then, on the other end of the spectrum, there's router Sam. Sam spots the F equals ma requirement and just clears the mathematical arguments for landing way too fast. Sam completely skips over verifying the structural safety regulations of the problem. So you see, the biggest challenge isn't just knowing the formula. Anyone can memorize a formula. It's deploying your knowledge, your application, and your analysis into entirely new, unexpected scenarios. When the examiner suddenly tilts that plane by 30 degrees and throws in a pulley for good measure, you cannot freeze up, you have to adapt. Moving on to Section 2, Core Theoretical Foundations. This is about so much more than just equations. We really have to shift our focus to the underlying architecture of these mechanics problems. If you want to stop making those frustrating, careless errors, you have to build a safer, much more robust conceptual approach before you even think about picking up your calculator. So the crucial point here is that top-performing students build a deeply connected understanding rather than just blindly memorizing formulas off a cheat sheet. The theoretical architecture of Cambridge Topic 4.4 actually rests on 3 pillars: precise definitions, causal relationships, and evidence-based reasoning. Let me give you an example. If you don't fundamentally understand that weight equals mass times gravity is just a specific real-world application of F equals ma, where gravity is your acceleration and weight is your force, you are going to misinterpret the radar signals the second the questions get tough. You absolutely need to reason through the problem with solid evidence, not just randomly plug numbers into a machine and hope for the best. Let's see how this builds your score. You have candidates providing isolated, narrow topic answers versus candidates making broad, cross-topic connections. The Cambridge Principal Examiner reports explicitly state, time and time again, that integrating syllabus areas yields significantly higher marks. If you're operating like router Alex, isolating Newton's laws entirely from the rest of your mechanics syllabus, you're practically flying blind. You must connect F equals ma to your kinematics equations, your SUVAT equations, and your work energy principles. The really high-scoring candidates? They instantly recognize that an acceleration found using F equals ma in part A of a question is the exact same acceleration they need to find the final velocity in part B. It's all connected. Section 3. The method mark strategy. This is where we talk about hacking the grading system. I want to introduce you to a concept I call the fuel to mark budget. Here in the exam tower, we know for a fact that the process you write down on your paper is just as vital as the final answer you inevitably double underline at the bottom. We aren't just hunting for accuracy marks here. We are actively, aggressively hunting for method marks. To absolutely maximize your fuel-to-mark budget, you must follow the standardized sequence that examiners explicitly look for. Let's walk through it. Step 1, identify key elements. This means draw the free body diagram always. Step 2, apply relevant principles. Explicitly state F=ma before you shove any numbers into it. Step 3, execute the analysis with clear sequential working. Step 4, verify your results. Ask yourself, does a negative acceleration actually make physical sense in this specific scenario? And step 5, present it in the appropriate format. This sequence right here, this is your glide slope. If you skip these steps, like Router Sam rushing the approach and doing all the math in his head, you will lose the method marks entirely. And the crazy part is, even if your final mathematical destination is perfectly correct, without the flight log, the examiner simply cannot give you clearance for full marks. Now, let's look at the strict presentation conventions that actually guarantee those method marks. I'm talking about proper headings, correct terminology, appropriate formats, and clear annotation. These conventions are your structural safety regulations. Ignore them and you just drop easy, high-yield marks for absolutely no reason. Oh wait, tower transmission check. Before we clear this response for touchdown, we need to ensure your transponder is fully updated. Hit pause, subscribe to Ace the Exams at Ace the Exams right now, and turn on all notifications so you never, ever miss an emergency broadcast like this one. Okay, transponder's updated? Great, back to the radar grid. We are moving into Section 4, Systematic Problem Solving. Deconstruct, solve, and evaluate. It's time to move to the practical application phase. When a high-tariff, multi-body system question inevitably appears on your paper, I want you treating it exactly like an air traffic control checklist. You do not panic, you process. Let's run a live audience tracking assessment right now. I want you to imagine a complex text data map right in front of you. Let's say it's a particle on a rough, inclined plane attached to a pulley, and you have a 60-second visual timer ticking down in your head. You need to isolate the primary trend variable. Walk through this procedural framework with me, and I'm purposely slowing down the pace here to reinforce the strict discipline required. Step 1, deconstruct the question, line by agonizing line. Step 2, extract the relevant data. What exactly is the mass? What is the specific angle? Step 3, select the analytical framework. Decide right then to resolve your forces parallel and perpendicular to the plane. Step 4, execute with perfectly clear notation. Step 5, present your terminology perfectly. And hey, if you encounter an unexpected structural block mid-paragraph, you deploy a formatting template, like the PEL method, to guide your sentence smoothly back onto the glide slope. State your point, provide your equation, evaluate the variables, and link it back to the question being asked. Then, as you lock in your final answer, you have to remember to evaluate your evidence quality. You must be able to identify limitations, hidden assumptions, and alternative interpretations. Top-scoring candidates don't just act like mindless human calculators, they demonstrate real evaluative thinking. For example, if the problem implies a particle model, you are inherently assuming air resistance is negligible. Knowing and explicitly justifying these decisions with evidence proves to the examiner that you have absolute total mastery over the airspace of Topic 4.4. Almost home. Section 5, the top 3 examiner alerts. Let's clear the debris on the runway. Listen up, because I am really increasing the vocal urgency here to share the most critical warnings pulled directly from Cambridge Principal Examiner reports. These are the exact traps that cause candidates to crash land their grades. Now, what's genuinely fascinating about this is how completely 100% avoidable these 3 common crash landing errors actually are. This is literal debris on your runway. Mistake number 1, confusing cause and effect. Mistake number 2, forgetting to check format and presentation. Mistake number 3, answers lacking specific context. Right now, as part of our interactive workshop, I want you to mentally pull up your very last mechanics mock exam. Try to find the exact line in your own sample answer that violated these safety regulations and drop points. Did you just write an equation down without any context at all? Because if you did, that's debris on the runway. Let's break down that number 1 mistake, visually isolating the cognitive traps students consistently fall into. Think about the cause, the actual physical force being applied. Now contrast that with the effect, the resulting acceleration of the object. When you write down F=ma, students constantly and mistakenly treat ma as if it is a physical force actively pushing or pulling on the object. Listen to me. It is not. Force is the physical cause. Mass times acceleration is simply the mathematical measurement of the resulting effect. Do not, under any circumstances, draw ma as an active force arrow on your free body diagrams. Keep the cause and the effect totally separated in your mind and completely separated in your equations.
I am officially flashing the amber warning light in the tower for this next one. Candidates consistently confuse key terminology. You must always define your terms. Please do not use the word mass when you actually mean weight. Mass is a scalar quantity measured in kilograms. Weight is a vector force measured in newtons, calculated by W equals mg. If you are writing out an extended response to explain why a particular system is in equilibrium, you absolutely must define your terms precisely before using them, or the examiner will strike down your method marks without a second of hesitation.
Let's bring the energy back up for an empowering close here. Router Alex and Router Sam have successfully corrected their vectors. They listened to the tower, and we are logging a successful full-mark landing sequence. Remember this quote: top-scoring candidates demonstrate evaluative thinking by questioning assumptions. This is the exact mindset you need to adopt. When you truly master F equals ma and weight equals mg, you are just blindly memorizing operations anymore. You are learning to read the underlying physics of the problem like an expert reading a radar screen. You start anticipating the tricky variables and adjusting your approach flawlessly before you even hit turbulence.
I'm going to leave you with this final provocative thought to inspire some critical self-evaluation. Next time you sit down and solve an F equals ma problem, I want you to ask yourself, what hidden assumptions are you making in your working? Are you just assuming the string is light and inextensible? Are you blindly assuming the pulley is perfectly smooth? Recognizing those hidden assumptions, that is exactly how you bridge the gap from a B grade straight to an A star. That is your fuel to mark budget formula absolutely maximized. Now, I need you to subscribe to Ace the Exams at Ace the Exams right now. Enable that notification bell so you never miss a transmission from the tower, and leave a comment below sharing which Cambridge paper gives you the most anxiety. We'll get to work and clear the runway for you in our next masterclass. Exam Tower, over and out.